So how are those projects going? I noticed on my calendar, as I'm sure you noticed on yours, that next Tuesday, a week from today, is when the Midway progress reports are due. And I'm very much looking forward to seeing the Midway progress, how things are going. We've gone a little easy on you in terms of other homework since the midterm, as you've noticed. We are going to have some what I would call lightweight homework for you. We'll hand it out probably Tuesday, the day you turn in your Midway report. And we're trying to make this the second half of the semester homeworks lightweight in the sense that we know that you're going to be working primarily on those projects. But we want to make sure that you have a chance to review the material that we've been talking about in lectures because, you know, of course, when the final exam comes, we're going to have a whole semester's worth of material to cover. And so what we're trying to do is put together a homework assignment where taking it is a little bit like taking a midterm. You know, like if you know all the answers in 80 minutes, you're done with the homework and you're out of here. Except like, unlike the midterm, if you're not familiar with all the answers, you still have extra time where you can work on it to figure them out before you turn in the homework. So that's the goal. Today, I want to finish up our discussion of different kinds of latent variable models, dimensionality changing representation learning approaches by talking about two more of these briefly, and then just make a beginning, if we have some time at the end, on kernel methods and kernel regression, which is will lead into our discussion on Thursday about support vector machines and maximum margin classifier methods. So that's the plan. So let's start. So we've talked about a number of approaches to changing dimension learning representations, for example, PCA, neural networks, and so forth. And we pointed out that PCA was an example of an unsupervised approach in the sense that we're trying to learn with PCA a re-representation of the original data that will just minimize the error if we ever want to reconstruct that original data. Whereas a neural network was a supervised, or could be used as a supervised method in the sense that we're really trying to learn with a backpropagation neural network some mapping from an X to an output Y, and the hidden layer in that neural network re-represents the input X's, but does it in a way that isn't necessarily trying to minimize the reconstruction error of the inputs of the network, but instead is trying to minimize the error in predicting the Y's. So in that sense, supervised. And I just wanted to, there's one kind of widely known additional supervised method called Fisher linear discriminant. And I just want to take 5 minutes and tell you what the idea is, because you may well run across it in your reading of the literature. And it is kind of a basis for a collection of other methods that people develop. And the idea is very simple. So let's think about a supervised learning problem. We might have points, x's like the points in this plot, and we want to learn to classify them according to their y, which in this case is the color red or green. And if you look at that data, if you plotted that data yourself, you might think something like, Gaussian naive Bayes would work pretty well here, you might think, for example. But generically, the idea of a Fisher linear discriminant is that we want to learn a linear classifier for this function, but in a lower dimensional projected space. So we want to project these points into some other space that will make it easy to classify them. And if this is a very high dimensional original space, then projecting it into that lower dimensional space is also kind of a way of dealing with possible overfitting issues. Okay. So if we looked at, let's say, this left example first, and I asked you, well, this is two-dimensional data, obviously. Just x1 and x2 are the two features that describe each point. If I ask you, well, what would be a good single-dimensional space to project those points into, you might suggest something like this line that's here. Because obviously, if we project let's project one of these points. Let's take this one. If we go to project that into that one-dimensional space, it'll show up there. That is, each of these dots will be projected into that one-dimensional space by drawing a line from that dot perpendicular to this space. And that's what the dot product of the green dot vector onto the closest point on the line. Sorry, the projection from each green dot to the closest point on the line will just be move that point along the line that's perpendicular to our dimension. And so then you see, well, that'll be nice because now I'll have a one-dimensional data set. Everything will just every point will be described by just this one number. And I'll have a bunch of data up at this corner and another bunch down there, and I'll be able to easily make a linear classifier, like separating the points on one side of that line from the other. Okay, and then if I ask you, well, what kind of algorithm should we use to do that? You might well say to me, well, we could use PCA and just take the first dimension generated by PCA, that unsupervised learning method, which will first choose the direction of maximum variance in the data. And you can see as well as I can that that's kind of the line I've drawn. Except that PCA is ignoring the colors, it's ignoring the labels, right? It's just looking at the whole set of data and finding the direction of maximum variance. So I'd probably reject PCA as an answer to how should we make this up. Maybe a more reasonable thing would be to say, well, let's take all the points which have y equals red, and let's find the mean of those points. And let's find all the points that have y equals green and find the mean of those. And that might be like, here's a mean of one of those, here's a mean of the other. And then we could draw a line between those two means. That way we're at least coming up with an algorithm that looks at the labels. And in this case, that would be a pretty reasonable approach. In fact, it'd probably give a solution very similar to PCA's first dimension. But you see what I'm saying? We could, if we want to project these points onto a one-dimensional, lower dimensional, one-dimensional surface so that we can do a good job with a linear classifier, then somehow we want to choose a dimension that separates out the reds from the greens. Okay, so now this plot of data makes it look like maybe deriving that dimension by finding the mean of the green, the mean of the reds, and just drawing a line between them could be a good idea. But that's the reason that this second set of points is on the slide. Because if we were to use that kind of approach here, we might say, well, the mean of these red dots is around here. The mean of the green dots is somewhere around here. And so we might get a line like the one shown there if we use that approach. But really, that's not such a great line if we're trying to get a linear classifier because, you know, obviously this red dot here will project onto this point. This green dot will project up here. So will this one. Here's another green one. So there's no place where I can draw the line, or sorry, no place where I can draw my threshold on this one-dimensional line. Couldn't draw it here, for example. Well, I could, but if I did, I'd be misclassifying the red points, a couple of these red points. If I drew it over here to not misclassify those, I'd be misclassifying some green points. So that's really not the world's best line. Now, does there exist a line that can, a one-dimensional vector we can define such that projecting these points onto that one-dimensional vector allows perfect classification of the training data? Yeah. So all I have to do is tip that line up a little bit. For example, if I pick, say, this line, I'm golden, right? Because now all these green points, well, they all kind of cluster here. Nicely, all the red points are here or north. And so I can just draw my classification threshold here and say, well, these are going to be red, these are going to be green. I'm good. So this is really the kind of line we'd like in this data set. And so our kind of intuitive idea of why don't we define our dimension by, number one, computing the means of the points in the different classes, the two classes, and then number two, draw a line between those means and call that our lower dimensional, single dimensional representation of the data. This makes it clear that that's not always a good idea. So what would we really like here? Think about it, it's pretty obvious. What we'd really like here, or what this illustrates that we'd like in general in both cases, is not the line that connects the means of the two clusters of points, but the line such that once we project the points onto the line, it does the best job of separating them. That's the line we'd really like. It's the one such that after projecting our original points into that lower dimensional representation, we can find a good linear classifier. And that's exactly the idea of the Fisher linear discriminant. In fact, it uses exactly that objective. So wow, did I really? I see. Oh, I see. Okay, so the objective function, and I'm not going to, like I said, I just want to spend a few minutes giving you the intuition. We're not going to go through the details of deriving this, but the objective function that the Fisher linear discriminant optimizes when it chooses a single dimension to project those data points onto is to pick the projection, the weight vector, W, that maximizes the distance between M1 and N2. Those are the means of the projected points, not the points in the original space. So M1 is the mean of all the green points, let's call that class 1. It's the mean of all the green points once they're projected onto our into the new space. M2 is the mean of all the other colored points once they're projected onto the space. And so we're trying to minimize the square of the distance between that mean divided by, well, S1 and S2 are the standard deviation of the red points and the green points, again, once they're projected onto that plane. So if you think, if, for example, if we can arrange so that these projected points onto this dimension are Gaussian distributed, for example, then this is going to give us the optimal, the Bayes optimal classifier, because out of all the possible dimensions that we could project things on, this is going to give us the one that maximizes the distance between the means of those two Gaussians, and actually not just the distance between the means, but normalized by their standard deviations. Okay. So intuitively, it makes a lot of sense. The math is not that hard, but I don't want to take our time here today to go through it. So the thing that I want you to just know that here's another way of projecting data into a lower dimensional space that, like the neural net approach, uses the labels of the data to decide how the input data X's are going to be re-represented. And B follows this, very common sense kind of idea that the objective we'd really like to optimize when we pick our new dimension is how separated the two class points are in the projected dimension, and that's the right objective function to be solving for. Okay, question?
Either a generalization to multiple dimensions. So this is the case of running.
Yeah. So this is a simple case, and this has been generalized in a whole bunch of ways. So you can generalize it to multiple dimensions. Okay. And in general, see, the cool thing about taking this course, by the time you get out of this course, you're going to be thinking of learning problems as, if you have to design your own learning system, you're going to be thinking, oh, what's the objective function I should be optimizing? And what's the representation of the learned function that I should be using? Those are the two key design questions when you have to design your own learning method. And so, as the semester has gone on, we've shifted more toward thinking about these algorithms in terms of what's the representation and what's the objective function that we're optimizing. And I think that's a nice, clean way to think about the design space of machine learning algorithms. Okay? So, different, unless anybody has any other questions about Fisher linear discriminant, this is a simple idea, but a nice, clean one. Okay. I didn't really want to start here. Oh, I see. Somehow my slides got confused and somewhat out of order. Let me just scan ahead and see where we are. I see. Okay. My apologies. My slides got... You know what? I can fix this. Give me 1 sec. Okay, sorry about that. So I want to talk about another approach which, to again, learning alternative representations of data. This one you may have heard of is called latent Dirichlet allocation, sometimes. Mostly called that by people who like a lot of syllables in their words. It's called LDA by some people, which stands for latent Dirichlet allocation, and has the unfortunate feature that it is an acronym that already was given to linear discriminant analysis, so it's a very confusing acronym. But you'll hear it called by either of these names. But the idea is this. It's a way of defining probabilistic graphical models, Bayes nets, like we've talked about so far, where we use the BayesNet learning procedure to learn a new representation of the data. And a kind of prototypical example of this is to apply it to collections of text documents. And when we talked about in this class training classifiers of emails and different kinds of documents, we used what we call the bag of words approach, where we said, well, let's represent every document that we're trying to classify, the X, as a collection of features where the features are positions in the document, and the value of that feature is which of the 50,000 words in English occurs in that location in the document. And when you did your homework on that sort of thing, you used a multinomial distribution to characterize that. And so in that sense, we were using the bag of words in the document as the raw features. So that's a good thing to do, especially if you're training a classifier and you have a lot of training data. But that can get you into trouble if you're training a classifier and you don't have that many documents, because then you have this problem that you don't have that many examples of each of the 50,000 words. So you don't really get very good probability estimates for your naive Bayes classifier, your logistic regression classifier, whatever you're training. And so the idea of LDA applied in this particular example is that let's learn, instead of saying that in the naive Bayes model, that each word is generated from some distribution that's conditioned on the label of the document, let's instead add an intermediate layer. Let's say we have a label for the document, but instead of just saying our BayesNet will generate directly the words from that label, let's instead have it generate some intermediate features of the documents, which we'll call topics. And they're sort of literally discussion topics that are being discussed in this document. And then given a topic like maybe this, here's a document, let's see. Suppose I have a document that's about hockey games in Pittsburgh. So there might be a topic about hockey that it's discussing, and some of the words in the document will be generated by that. There might be another topic that's also discussing Pittsburgh. And there might be other words in the document that are related to that topic. And of course, there could be some that overlap that are related to both topics. But the idea is that these, by introducing this intermediate set of features, we get in a sense, an alternative representation of the document, not just as a bag of words, but also as a bag of topics. And so what this slide is showing is a collection of such topics that were learned from a large collection of texts. This is from some work by Josh Tenenbaum. But given a very large collection of text things, each of these columns represents each of these columns represents the words generated according to by one of the topics. So there's a topic, for example, that generates words like these, which seem to have to do with fish and being in the water, as opposed to another topic that's generating words like these and so forth. Okay? So let's look at what that model is. Before we do, I need to explain this weird notation. So, and this is worth knowing too, because you'll see this kind of notation for Bayes nets also in the literature as you read. This is called plate notation, and so just a compact way of representing a big branchy Bayes net. And the way you read this is you say, well, if I were to draw this in standard form, I'd say, well, there's a variable alpha, which is generating d copies of the theta variable. Let's call them theta 1 up through theta d. And then each of those is, and D, by the way, stands for document in our topic model. And so for each document in our set, we're generating some random variable theta. And then for each of the n words inside each document, we're generating Z, I guess I'll have to call this 1, 1 and this Z 1, 2. Up to Z1 ND. And similarly for these guys, they generate their own Z21, Z22, etc. And then the Z's generate W's, one for each. Okay, so you get the idea. So I could draw this as a standard BayesNet, but it'd just be a big branchy tree. And so the idea of plate notation is we say whatever we want. We just draw a box or a plate around something. We say they're going to be D copies of this. And so there they are, theta 1 through theta D. And then within the scope of that, we're also saying for each of those thetas, there's going to be n sub D copies of this internal structure with the Z pointing to the W's. So it's just a way of drawing compactly tree-style Bayes nets. But now let's look at this Bayes net. This Bayes net actually, W here stands for the words in my document. The Z's are the topics. That's the random variable that defines which topic. That's the latent unobserved variable. And it's an integer valued variable. It just, if I allow, say, 20 topics, then Z can take on the values 1 through 20. And depending on which of the topics I choose, like maybe that one that was about swimming and fish, if I choose that topic, then I'll generate a word according to the probability distribution over words given that fish, water, swimming topic. If I choose a different topic, then I'll generate words according to its distribution. And then what is theta? Theta is the distribution of topics. For one document. Well, I'll just call it document D because theta 1 is for document 1, theta 2 is for document 2. Of course, each document will be might be on a different topic or a different mixture of topics. And what theta is, it's a distribution over, suppose I allow 20 topics, then theta is just a distribution over those 20 possible values that Z could take on. And so, and then what is alpha? Alpha is just the prior on theta. So in other words, according to this Bayes net, if I want to generate a document, if I've learned all the parameters of this Bayes net, and I want to generate a new document, what I do is I start with alpha, which gives me a prior on the thetas, and I just take a random draw of my from alpha, and I generate the theta that I'm going to use for this document. That theta, again, will be 20 probabilities, one for each of the possible values Z the topic variable could take on. And then, for each word that I want to generate, I randomly generate a Z topic for that word, given theta, the distribution of topics for this document. And then given that topic, maybe it's the swimming fish one, then I generate a W according to the distribution for that topic. Now I want to generate word number 2. I go all the way back up to picking a new z. I'm stuck with this theta because I'm still inside the document. I use the same theta throughout the document, but theta is a distribution on topics, and so each time I generate a word, I draw a z value from theta, and then I draw a w given z. Okay? And this, I'm just saying what you already knew because you know how to write down the joint distribution for an arbitrary BaseNet graph, and that's all I'm saying here. It's the same joint distribution you would have said if I asked you. Okay, so in that sense, these topic variables are a latent set of variables that redefine or re-represent in some sense the document in terms of abstracting it up to this level of topics instead of words. And of course, like any BaseNet, if I have trained it and now I have a particular document, then I could say, well, my W's are all observed. What's the probability distribution on Z's given these observed W's? It's an inference problem for BaseNet, so I can re-represent the document by solving that inference problem for this BaseNet. Okay. And there's just one detail I left out here when I was describing the plate notation that I realized I should be sure to tell you, which is when you use this plate notation, it's saying more than, here's the structure of the BaseNet. It's also saying there are a lot of shared parameters in that BaseNet. So in particular, when I say that Z depends on theta here, and so theta has a lot of descendants, if this were an arbitrary BaseNet, then of course all these Z variables could have different conditional probability tables saying how they depend on their parents. But if it's a plate, that means that the probability table on this edge and this edge and this edge are all shared. They're all the same. So these are literally copies, not just of making another copy of a Z variable, but also using the same distribution, Z given theta. Okay, so all the copies in this plate notation mean that they're the same parameters.
How about the other variables on the same level?
The other variables on the same level, yes. So these, all of these are also shared.
I mean, does the parameter for Z21 equal the parameter for Z11?
No. So this parameter is different from that one, but shared with this one. So when we say we're making, for example, D copies, we mean for each time we make a copy like that, then we copy the variables and the conditional distributions, share the tables there. But then when we nest and go inside, we get a different one. Okay, so let's see. What should I say about this beta and the theta here? The beta is really just one of the parameters in the model, as are alpha and theta. Those are just probability parameters. And we haven't generally in this class, when we draw BaseNets, we've often just not bothered to make the parameters part of the BaseNet. But in this case, in some cases people do. And I got this slide from a paper published by Andrew McCallum, who did want to make this explicit. So beta is essentially a way of saying what is the probability of W given Z. And beta is a prior on these different phis. There are T of them for the T topics. And so essentially each one of those says if Z equals some topic, then here's the distribution of W on Z. So these are just essentially the parameters that make the distribution of W given Z. just as alpha are really the priors on theta, and we might also have just said that's part of the conditional distribution of theta. Okay. But that's another thing you'll see as you read papers in the literature is that there's not a single golden only way of drawing these Bayes nets. Sometimes people make the parameters part of the Bayes net as explicit nodes. Sometimes they just don't bother to write them with the idea that everybody knows they're in the conditional distributions tables anyway. And here it's handy to make at least alpha and theta explicit because it helps you understand what's shared across documents and what's not. Okay, so that's the notation. So this is just standard Bayes net stuff. And for example, if here's just another diagram from another paper also talking about the same kind of topic model. And just as you would do if we gave you that Bayes net on a final exam and asked you to write down the joint distribution over those variables, you'd write down something like this. If I ask you, given alpha and beta, what's the probability of W? You'd say, well, according to that Bayes net, I start with alpha, I generate a theta, so I'm going to integrate over theta. And then given a theta, I'm making n copies of the words, so I'll take the product over all the words. W here is a vector of words. I'll sum over the topics, and I'll get the probability of any given topic, z sub n, given theta, and then the probability of word n given topic z, and the parameter is beta. So it's just a standard kind of joint distribution. So that's the probabilistic model. It's just one Bayes net that you could make up. But this one's kind of interesting because it does give us these kind of learned topics that capture the distribution on words in different documents in terms of these intermediate topic clusters of words in a sense. Uh-huh.
In the previous page. So this, there's a term of P of Z and given theta here. So that does not depend on which document it is. So in the previous page when you said that those arrows on the same level are not shared, what does that mean?
Yeah, let's see. You're raising a good point, which is, where is m in this expression? And I don't see it. It looks to me like this is saying, if we have a single document and we want to give a single arbitrary document, and we want to get the distribution on the vector W of words in that single document, then here's how we will do it. Yeah. If we wanted an expression for the m different word vectors in m different documents, then we would...
We consider the differential for this m generation the same. That's the question.
Yes, we do. No, we don't, because we're sampling... this term is in there. So each time we generate a new document, we'll be looking at a new, if we were to do this as a generative model, yeah, we'd be drawing a new theta for each one.
Yeah, I mean, if, like in the generation of two documents, if we happen to have the same data, then do we have the same piece of Z given data?
Ah, okay, yeah. So you're asking, your question is very interesting, because you're saying, if we had two documents, would we have the same theta given alpha in those two documents?
No, the same P of Z given theta. There's one layer.
P of Z given theta.
Yeah. But because in the previous page you said they're not.
Ah, my mistake. So maybe this is the reason Andrew drew it this way. Yeah, yeah. So to think clearly about this, we need to separate out two things. One is, what are the values that the random variables take on during, in a particular document, in a particular, more generally, draw of the joint assignments of all the random variables in the Bayes net. So of course, every time we see an example that corresponds to a different draw of the values in the random variables, and even though we might have a single Bayes net, we take several draws, of course, we get different values of the random variables. And so when we talk about different documents, M, from the single Bayes net,
so what I mean is that the small dashes and the circles should be shared.
no, the small dashes and the circles must not be shared. So theta 1 and theta
It
2,
can be different if theta 1 and theta 2 are different, but they are from the same small CPD, from the same small table. They're just different rows of the small table.
no, they're different values because so they're literally draws of the, this is a different kind of Bayes net because we're now talking alpha and theta are actually the parameters of the distribution. And what this thing is saying is that for every document, we generate a different, literally a different theta. And what is theta? Theta is this vector of 20 probabilities corresponding to the probability of drawing z equals 1, z equals 2, z equals 20. And on every document, we're going to draw a different theta that sets up different probabilities of those different topics. What do we draw them from? We draw them from alpha. So we have this prior over the probability distributions on topics. And each document we get to draw from that same prior a different probability distribution over topics. So for one document, we might have high probability that it'll be talking about water, and low that it's talking about hockey. And a different one will have a different thing. And so those really are different parameters. And now the z's and the w's are more like the variables that we had talked about before. And
Okay, let's take this offline.
yeah, so, but you see, it's a little different because some of the nodes here are actually parameters that are controlling distributions of other things. Okay, so let's see what we do with this. So I mentioned before that there are these, if we run this on a large collection of text, the interesting thing is that we get these different topics fall out. And if for each of those topics, if we look at, say, z equals 16, which would be one of these columns, we can then say, well, what's the probability distribution over words once we train this network for z equals 16? And let's sort the words from most to least probable. And so that's what these columns are doing. So each column corresponds to some value of z, and then ball is the highest probability word given that z equals this column. And so one thing you notice here that's kind of interesting, these words in red actually occur in many columns. So each one of these topics is a full distribution over words. And so the same word can, in principle, be generated with different probabilities according to the different topics. But what's kind of fun is you see this gives us a way of approaching the question of resolving word sense ambiguity. So this word field, for example, has one meaning if we're talking about baseball games, has a different kind of meaning if we're talking about magnetism. But that token can get generated from either topic. So it's kind of an interesting side effect of doing this. So I guess this is kind of the summary. So these topics reveal categories of words that kind of group together within the documents. And even though there are 10 to the 5th words in English, often if you characterize a document with on the order of 100 or so topics, you can get a pretty good characterization of that document. And this point is that when would we want to use this? Well, one thing that is kind of interesting of these is that because they abstract above the level of individual words to the topic, they kind of smooth over synonyms. Right? So if I was talking about baseball, I might call somebody the pitcher or the left-hander or the hurler or the strikeout artist or so forth. But if I could learn these topics from a large collection of text, then presumably all those words I just said would be affiliated with high probability with the same topic. And now if I went to classify, say, a headline of, if I wanted to classify very short documents like headlines of newspaper articles, if I train and test on short documents, I'm going to get into this. Maybe I've never seen the word hurler before in a labeled example. But the interesting thing about these topic models is it's an unsupervised method. So I can train these topic models over a very large unlabeled collection of texts. That could reveal things like pitcher and lefty and strikeout artist and hurler are all sort of within the same topic. And then if I have a small amount of labeled data, especially with short documents like headlines, then having these kind of topics can be very useful for essentially extrapolating to synonyms that weren't part of the training set. So that's kind of the intuition behind, one of the intuitions behind why this is an interesting approach. Okay, so you get the idea of these topic models. Now, there's one other thing I wanted to show you, which is, I think, very cool. This is some work done by Andrew McCallum, former postdoc here at CMU, now a professor at University of Massachusetts, Amherst. And so he got the idea that, well, why don't we use these kind of probabilistic topic models to do a new kind of social network analysis on email collections. So he was thinking about this problem at just about the same time that Enron got sued by the Justice Department for being such a dirtbag company. And as part of the law case, the Enron email corpus was subpoenaed by the Justice Department and became part of the public record. So Andrew got interested in doing social network analysis on email, and he ended up using the Enron email corpus. Okay, so what did he do? Well, here's the topic model we were just talking about. And again, this just says if we want to generate the words, the observed words in some document, we will, for that document, first pick theta, a distribution, probability distribution over the, let's say, 20 topics, z. Then for each word, we'll pick one of those topics from theta, and then given that topic, we'll generate a word according to that topic. Now, what did Andrew do? He said, well, let's modify this according to this diagram on the right. He says, well, a word gets generated, okay, by some topic z, just like before, but that topic actually depends on who the authors and the recipients of the mail are. If it's you and me, it's probably going to be about the topic of the machine learning class, something like that. If it's you and your mother, it's going to be about some other topics. So he said, let's build a Bayes net where the words depend on topics, but the topics don't just like come out of some generic theta distribution, they're actually conditioned on who is the recipient of the email. And that's conditioned on who could be the recipients, who are the known recipients of, oh, sorry, this is one recipient. These are all the recipients of the email. So that's why this is observed. That's why it's shaded in. And we also know who's the author. So basically he says, okay, the observed things are not just the words, but we observe the words, the author of the email, and the list of recipients. And then from that, we're going to generate a topic by, number one, picking one of those recipients according to some distribution. And then the recipient and the author will have a author-recipient specific distribution on Z. Okay, so reasonable model. Basically, it's just saying the words you talk about depend on who's writing the email and who they're sending it to. But now we've got these latent topics that are now going to be, we can now ask what's the probability of different topic given a particular author and recipient? What do different people talk about to each other? So you get the model? Okay, so he trained this model on the Exxon email, about 250,000 emails. And here's what comes out. It's actually kind of interesting. So, for example, here's one of the topics, topic 17, which has high probabilities with these kind of words: attached, agreement, review, draft. And this topic is generated by author-recipient pairs like Nemec and Teicholiz, or Nemec and Witt, or Teicholiz and Nemec. Okay, so he sends to him this emails with that topic, and in the other direction we also see that topic being discussed. That guy sends also to this person, and so forth. On the other hand, here's a different one that's about game draft week, team, pick. These people do that. And these people, who knows? Well, he thinks maybe it's about scheduling stuff. Okay, so these are the kinds of topics that show up in the email. And again, now they're conditioned on particular author-recipient pairs. So you may know that the reason Enron was sued is that they were an energy company that was doing suspicious things to price their energy. And so it's interesting that some of these topics actually relate to like power, market, customer, cost, price systems, and between these particular people. But if you go to the directory of Enron, for example, Beck is the Chief Operations Officer. So he's involved in these topics about operations, team, office. Here's some people who were government relations executive, VP of regulatory affairs. So like Steffi's VP of regulatory affairs, the topics in his email involve these kind of things. Steffi's, Shapiro, regulatory affairs also. So it's kind of interesting that you start to see with this kind of analysis, and again, imagine you're the Justice Department. You have 250,000 emails you just subpoenaed, and you don't really have time to read 250,000 emails, and if you did, you wouldn't know how to organize it. So this kind of an approach can actually be a very interesting scheme for doing an analysis on a very large corpus of documents, emails, and then saying things like, well, I'm interested in ones that were sent by Dasovich that were on the topic of power markets. And so this is a way of kind of finding those things probabilistically. So Andrew also did what some people call link analysis. So some people who do social network analysis think of the world this way. They think each of us is a node in some graph. There's an edge between us if we interact somehow. And then we can look for cliques in that big graph, or tightly connected subsets of nodes, and those are social groups in some sense. And quite often that analysis is done without really being very precise about what is the meaning of an edge, or just saying there is an edge, and maybe the edge is yes if you phone called with me, or if you emailed with me, or if we went to the same birthday party, or whatever. But what's interesting about this kind of analysis is that it gives a very precise characterization of the edge in this email graph, where each person is a node, and each edge now characterizes the probability distribution over topics and words in the emails between these two nodes in the graph. So it gives a very different and more precise kind of characterization of the edges in that social network graph. So if you do the first kind of traditional social network analysis, just treating this email collection as each author and recipient is a node, and there's an edge if we share email, then you find that if you take, say, these 16 people and ask which ones share emails, then the black places are where there are a lot of emails being shared, and you can kind of see who groups with who in terms of just volume of shared emails. But now if you do this probabilistic model analysis and you ask, let's not color the nodes by how many emails went between these people, but instead by how similar are the topics that they author when they send to the same person. Then you see a very different set of black patches than you see based just on the volume of email. Okay, and so this is capturing something about what are people talking about, and are they discussing the same things if they're both emailing me, as opposed to do they share email with each other. So it's a very different kind of way of looking at things. And if you, for example, look at this one, Tracy Giacombe here. Do I know who she is? Yeah, Tracy Giacombe was had a position secretary. McCarty had a position vice president. If you look at the links, the analysis of the two of them, you see they shared a lot of emails, but they discuss very different topics. So possibly this person was discussing scheduling things, whereas this person was discussing the topic of the meeting, for example. So this kind of analysis can give a very different insight into the social network and what's going on and who's related to who, how. And again, this is through kind of this notion of topics as an abstraction, a re-representation of the ground level words in a document. And so this ties into the theme of the last few lectures, just in the sense that we can also use these probabilistic graphical models to learn latent variable abstractions of the observed data, tuned by the design of the Bayes net to characterize certain kinds of information. Like in this case, we're getting essentially a characterization of the topics in these documents tuned for the purpose of maximizing data likelihood when we condition those things on the authors and recipients. Okay. So there's another example. All right, so that brings us to the end of our discussion of learning representations. And I probably don't have to belabor this. I think you see that we've actually talked about quite a few of these methods now. But one reason I decided to spend 3 whole lectures on this kind of work is that I think it's one of the more dynamic parts of the field of machine learning right now. There's a lot of work, a lot of interest in learning representations and also in what people call multitask learning, learning different functions that might share the same representation. So I think over the last 5 years, there's been kind of an increase in work in this area, and I think that'll probably continue into the next decade. So it's a hot area. Okay, so any comments, thoughts, questions on this before we leave this topic? Okay, then I want to move on to the topic of kernels and maximum margin classifiers. It's not unrelated to this idea of learning representations or working with data that's represented in a couple different spaces. So we're going to start with talking about kernel-based methods. And here in a nutshell is the idea of kernel-based methods. I wish I had a blank. Oh, I do. Well, I'll use physical space. The idea of kernel methods is this. Suppose we have data in some, I'll call it the low-dimensional original representation, maybe just in 2 dimensions. So we have points in 2 dimensions. We want to learn a classifier. And if you think back on the semester, you realize one thing we're really good at is learning linear classifiers. We have a lot of good methods for doing that. We have a little bit of trouble when we get into nonlinear classifiers, especially because a lot of them have non-convex objective functions. So we worry about getting the optimization solved globally, and often we end up getting trapped in local minima, as we do with neural networks, for example. Okay, well, we're good at linear classifiers. And so the question that kernel methods try to answer is, if we have some original representation where we believe a linear classifier will not cut it, that a linear classifier is not the right thing here, it's going to be some higher dimensional nonlinear classifier, then let's take the following approach. We will project the data points in this 2-dimensional original space into some higher dimensional space. Like instead of 2, maybe 20. And that will allow us to calculate, we can make up 20 features out of these 2 observed features and call each of them a different dimension. So for example, if the original features are x1 and x2, maybe they're real values. It's a Euclidean 2-dimensional space. Then we might say, well, okay, in my 20-dimensional space, I'll have x1 times x2. I'll have x1 squared. I'll have x2 minus 1 x1 squared. I'll have e to the x1. I'll have e to the x1 times e to the x2. I can make up features, right, and project it into a higher dimensional space. And then try to learn a linear classifier up in that higher dimensional space. And because that's an enriched space, for example, if I even just one of those features that was nonlinear, like x1 times x2, if the correct classification rule is x1 times x2 must be greater than 3, that will not give us a linear surface in the original space, but it will give us a linear surface in my 20-dimensional space. And so you can see that they're going to end up being decision surfaces in this original 2-dimensional space that were not linear, that will end up being linear in the exploded space. I'll call it the exploded space. Okay? So, I mean, it's just kind of, it's a simple idea. And so if we could find good spaces to operate in up there, we could learn linear classifiers. Okay, and we will. That's where we're headed. Now, it turns out that there's actually a wonderful mathematics around this problem that shows, for example, that for certain types of projections that explode our original data into this larger space, we can characterize the linear functions up here and the types of nonlinear functions down here that they correspond to. And furthermore, this is actually the most amazing thing to me. For many of the problems we're going to be working with, in fact, this is how support vector machines work, they learn linear classifiers up in some much higher dimensional space than we start with. But the amazing thing is they do it without ever having the algorithm explicitly transform the data up into the exploded space. Instead, they perform all their computations down in this little original space and thereby end up being much more efficient than if they actually exploded them into the higher dimensional space and learned the linear classifier up there. So we're going to be talking about kernel regression and kernel methods, including support vector machines. And kernel simply means a kernel is a function. Well, you'll see why this is important, but a kernel is just a function that I can apply to 2 points in my original space, whose value will be equal to the dot product of those 2 points if I explode them into the higher dimensional space and then take their dot product up there. That's what a kernel function is. And as we're going to see, it turns out that's an extremely useful thing to be able to do. And furthermore, we're going to be able to train linear classifiers and, in fact, linear regression systems in very high dimensional spaces by using kernel functions down in the original space to do the mathematics. So that's the full story of kernel methods. So we're going to get started in earnest on this next time, but I want to just start here getting us thinking about the notation that we're going to use and start with the problem of linear regression. And we're going to build a kernel regression method that just like linear regression in our original space, but we're trying to predict some y. Well, let's go back over. Linear regression we've talked about. It just means we're trying to learn some function where x is some set of features and y is some real valued number. Now, we just want to learn that function. And in the past, we said, well, it's a linear function. I'm going to use this bold as a vector. So if you see a bold thing, it means it's a vector or a matrix. In fact, uppercase means matrices, lowercase means vectors. So I'll say the function I'm trying to learn is of this vector of x1 through xn. It's just the linear sum of the weighted feature values, which we've talked about before. I'm going to introduce, this notation means literally the dot product. We can think of x and w here as vectors of weights and feature values, right? So for example, I could talk about the vector v, the vector w, as a column vector. That's just weight 1, weight 2, up through weight n. And if, in general, I'll use bold to represent a column vector, like that. And then I'll use T to mean the transpose and so the transpose of a vector is just rotating it so that the column becomes a row. And so this is just notation, but it's important because we're going to be using it a lot. So I'm going to say f of x, x again is the vector x1 through xn, is just like we said before, the sum of weight number 1 times x1 plus weight number 2 times x2. We can think of that as the dot product of these two vectors. And the dot product of this row vector with this column vector is literally this expression. Okay, so just kind of remind you of vector notation. And so then I could say, okay, so to restate the linear regression problem, I'm trying to learn this function by learning the weights W, the vector of weights W1 through Wn, so that we minimize the sum of squared errors plus some regularization penalty. It's what we've talked about before. This will be the y, of course, is the value we're trying to predict on the ELF training example. And of course, I'm going to predict it using this function here, which I can write this way, of course. So stating the problem, I'm just trying to minimize the sum of squared errors between my prediction for the ELF observed training example, which is x transpose times the weight vector, and the difference between that and the observed y for the ELF training example squared, plus my usual regression penalty term of penalizing the square of the magnitudes of the weights, which corresponds, as you know, remember, to a map estimate assuming a Gaussian zero mean prior on those weights. Okay, so that's just a way of introducing the notation. Now the next notation step I'm going to do is, this is kind of intricate way of saying what I'm trying to do. What if instead of summing over those training examples, let me actually just make y into a vector also. So say, well, there's y for the first training example. Here's the next training example. Maybe I have a total of m training examples. So I can rewrite this thing by saying I want y to be equal to the vector that I get if I multiply my weights, W1 up through Wn, by the different training examples. Right? So what should I put here in the first row of this matrix? The first training example, right. So this will be like the value of feature x1 for the first training example, x2 for the first training example, xn for the first training example. Down here I'll have the mth training example. All n features for all m examples. So each row here is going to be just one of my training examples. The dot product of the weight vector with row I will give me the will give me a single number, which I hope will be equal to the y that the training example said it should be. Okay, so it's just a way of writing this. I'm going to call this matrix X for obvious reasons. I'm going to call this vector Y, and I'm going to call this vector W. So now I can just rewrite this whole thing up here as y minus xw. And what I really want is the sum of, so when I multiply this times this, I'll get a vector the same size as y. I just want the the sum of the squared differences between those to be maximum, or I'm minimum, and so I'm going to be interested in the norm of that. It's just a notation for saying the sum of the squared differences in the two vectors. Okay? So this notation then is what we're going to be using, and it's a much more compact way of thinking about these things. But it boils down to the simple expression. Again, we're trying to learn a linear function, which we can write in our vector notation this way. And then we want to solve for the w that minimizes the sum of the squared errors plus the sum of the squares of the weight values. And this, again, this matrix X, the nth row of X is just the nth training example X. All right. So maybe this is a good place to stop. We're going to, if this notation is familiar to you, it'll be a breeze. If not, please spend 10 minutes looking at this and grokking it before our next lecture. You'll be glad you did. What we're going to show, the first thing we're going to show next time is that this, when we solve for these W's, we can express the weight W, the weight vector W, as a simple weighted sum of all the X's, which is kind of a surprising fact to some people. Was to me when I first thought about that. And then it turns out that's the key to being able to use kernel functions with dot products. So that's where we'll go next time.